everyone, welcome back again. We are going to start lecture 17, in which we're going to talk about two topics: cosmology, which is the study of the cosmos, and is there life in our universe besides us? Cosmology is what we're going to start with. This is the first half of the lecture. Our cosmology has to do with studying the universe, the cosmos. Surveys of the galaxy has revealed the existence of structures in the universe up to 200 megaparsecs. Are there larger structures? Does this hierarchy of clustering stars to galaxies and galaxies to clusters, to superclusters, to voids and filaments continue forever and ever? Astronomers think no. Astronomers use redshift surveys to construct 3D maps of the universe on cosmic scales, creating the Sloan Digital Sky Survey. It extends to about 1,000 megaparsecs, and many voids or regions of empty space and their resulting filaments, networks of strings of galaxies surrounding voids, can be seen on scales of a few tens of megaparsecs at large distances because the more distant galaxies are harder for us to see. But there is no evidence for any structures on scales larger than 200 megaparsecs. Even the largest object in the universe, the Sloan Great Wall, which is a large filament-style cluster of galaxies, can be explained as a chance superposition of smaller structures. Results of this survey and other large-scale surveys is that the universe is homogeneous. It's essentially the same everywhere, on a scale greater than a few hundred megaparsecs. If we look at a cube of 300 megaparsecs on each side and put it anywhere in the universe, its overall contents would look about the same. The universe also appears isotropic, or the same in all directions on these scales. We can count roughly the same number of galaxies per square degree in any patch of sky we choose to observe. This isn't to say that in our direct neighborhood it's isotropic and homogeneous. This is on the scales of 300 megaparsec cubes. The twin assumption of an isotropic and homogeneous universe is called the cosmological principle. Implications of this principle are that there is no edge to the universe. I mean, think about it. What would be beyond the edge? Are we thinking Looney Tunes, where once you go beyond the edge of the universe, you're in a space that's just white and you can open a door and go back into the universe? I don't think so. There also is no center to the universe. If there were, the universe would not look the same in all directions from any non-central point. We are not the center of the universe, but neither is anyone else. The cosmological principle leads us to a different problem. If everything looks the same, then shouldn't the night sky be as bright as the sun? This is known as the Olbers paradox, which is the difference between the prediction, it should be bright, and the reality, it's really dark. However, astronomers have observed proof that galaxies are moving away from us in the form of redshift, which is described as Hubble's law, which is the recessional velocity equals h times distance. Hubble's constant remains the same, 70 kilometers per second per megaparsec. This relationship has been used for determining the distance of galaxies and quasars. But it can also be used to help determine how long it took galaxies to get to their present distance from us. Take distance traveled by velocity. Velocity is Hubble's constant multiplied by the distance, and since the distances in the numerator and denominator cancel each other out, it just becomes 1 over Hubble's constant. This time is independent of a galaxy's distance. This is because the galaxies most distant from us, according to their redshifts, are moving 2 times as fast, making the time it took to travel was the same. This implies that in the past, everything was right on top of each other. That single point would have been enormously high in temperature and density. If at some point the universe, or the beginning of the universe, at that one point, it would begin to expand rapidly in all directions, causing the density and temperature to decrease rapidly as the volume increased. This event most likely was insanely violent, and scientists know it as the Big Bang. The Big Bang theory provides a resolution for Olbers' paradox, meaning that the universe may be infinite, but we see only a finite about. That which is about 14 million years ahead of us. It makes you think, what else is out there that we just haven't seen? Where was the Big Bang? Everywhere. The whole universe was in a single point. So if we were to think about Looney Tunes, where people end up out in this white screen space, and there's this little point in the middle, and they're like, oh, that's the universe. Okay. That's essentially what it is. No matter where in the universe we are, we will measure the same relation between recessional velocity and distance with the same Hubble constant. This can be demonstrated in 2 dimensions. So imagine a balloon that has coins stuck to it. Okay, it's not blown up yet. You just stuck a bunch of coins to a deflated balloon. That is your point of the universe. Now start to blow up that balloon. The coins will move farther and farther and farther apart, but you'll notice there is no center of expansion. Every point on the balloon looks the same as any other point from the perspective of each coin. If we were one of those coins, we would see every other coin moving away from us, and the other coins would see the exact same thing. The same analogy can be explained with the cosmological redshift that we see. Up until now, we've explained the redshift we see everywhere as the Doppler shift. However, it's not really a correct term because galaxies are not moving with relationship to the universe. It's more that as photons move through the cosmos, they are affected by the expansion of the universe itself, causing its wavelength to physically stretch. This means it's not due to its velocity, but rather to the changing size of the universe. We can reverse engineer this to actually determine the amount of expansion that has happened since the light was emitted in the first place. Will the universe just expand forever? This is a huge question. It's been a big question among cosmologists and astronomers who study the origin of the universe since the Hubble's constant has been found. And it's led to 2 major ideas for the future of the universe. 1, yes, it will expand forever. 2 is that the universe will actually collapse back into itself, resulting in another Big Bang. And with this second theory, it's believed that this isn't the first time we've had a Big Bang, that it just keeps happening over and over and over and over again. How do we even know that these 2 ideas work? Well, consider a rocket ship. When we launch, based on Newtonian physics, 2 things can happen. It could make it into space, escape our atmosphere, right? It could go past the escape velocity, or it could fail to reach the escape velocity and fall back to Earth. This can also happen to the universe. In theory, it can keep expanding forever. In which case, we move farther and farther from each other and other galaxies, and we kind of sort of just end up really alone, and we'll die in the cold blackness of space, never seeing stars because we're so far away from every other galaxy and star, with the exception of those within our own galaxy. Or the universe expands to a point, and like pulling a rubber band far enough, it snaps back. What determines the option here? Mass. Mass is what does it. The mass of a planet determines the escape velocity of a rocket, so the lower mass planet is easier to escape than a high mass planet. Ideally, you can put this same idea for the universe. The density of the cosmos is what's going to determine if it's going to expand forever or snap back. A high-density universe contains enough mass to stop the expansion and cause a collapse, whereas a low-density universe will be able to keep expanding forever. The dividing line here is the universe's critical density. The density corresponding to a universe in which gravity alone would be able to be just sufficient to halt the present expansion. With a Hubble's constant of 70 kilometers per second per megaparsec, this critical density is 9 times 10 to the negative 27th kilograms per meters cubed, which is a very low density. However, recent studies show that gravity may not be the only factor influencing these 2 options. What do you think it could be? Basically, what we're seeing right now is a high-density universe over time would eventually collapse, and a low-density universe would expand forever. But based on this assumption, we are here. What's your idea? What do you think will happen? And I want you to think about this the entire time as we learn more and more. Do you think we're just going to perpetually expand forever until we die alone and cold? Or do you think we will eventually collapse and this will just start all over again?
If so, do you think that there's evidence of previous universes from before?
Like I said previously, it's not just gravity that is influencing this. The shape of the universe is one of the other factors that will help determine the option for the future of the universe. There are 3 types of shape that cosmologists have come up with. The closed universe, in this case, the geometry that leads to ultimate collapse. But basically what it is you have a high density universe where space is curved to the point where it bends back on itself and closes off, making a finite size or a sphere. And the one unique attribute of this is if light goes in one direction, it will eventually come back from the other direction. If the density of the universe is below critical value, the curvature of space will curve like a saddle. It will create a negative curvature. the curving up in one direction and down in another. This is also known as an open universe. In this case, the universe will have a density that allows it to be below the critical value, allowing for it to just expand forever. And basically, you'll have a saddle shape. And then the last or intermediate case, our second case, is if the universe has a density equal to the critical density. There's no curvature at all, basically flat, and it's infinite. This essentially is the space that Newton would have known. The answer to which future will occur lies in the actual density of the universe. Measurements of luminous matter suggest that the actual density is only a few % of the critical density. But we know that there must be large amounts of what we call dark matter, matter that cannot be observed, but it is known because of its gravitational influence on other objects or other matter. Best estimates for the amount of dark matter needed to bind galaxies and clusters and to explain the gravitational lensing we see only brings the observed density up to about 0.3 times the critical density. Monitoring cosmic acceleration is another way that we can measure the behavior of distant galaxies, such as type 1 supernovae, standard candles. If the expansion of the universe is decelerating, as it would if gravity were the only force acting upon it, then the farthest galaxies had a more rapid recessional speed in the past and would appear as though they were receding faster than Hubble's law would predict. Basically, it would appear that they are slowing way faster than we thought, if you want to put it in a sentence like that. Here's a question. Do you think that's happening? We just learned that what we see in the distance is they're going 2 times faster than we are in expansion. If they were slowing down, they would be, quote unquote, starting to blue shift. So we wouldn't see red shift as much. We would see maybe green colorings or we're getting closer and closer to blue as it slows down and we are starting to catch up. Recent data, to try to clarify what this would look like, found something rather interesting. It appears the universe is actually expanding faster. Observations indicate that gravity is not the only factor determining acceleration and deceleration of the expansion. So the question is now, what is? It sounds like a B-rated horror film, but it's not. We call it dark energy. Cosmologists don't actually know what is causing the acceleration in our universe. Although whatever it is carries energy and it exerts an overall repulsive effect on the universe, making empty space expand. It is simply known as dark energy, and it is a huge subject of research and debate
amongst astronomers today.
Leading candidates for what dark energy is that it's an additional vacuum pressure force associated with empty space, which is effective only on very large scales and is known as the cosmological constant. This has gone in and out of favor since its determination by Einstein. So while models including the cosmological constant can fit the observation data, astronomers still don't really know what it means. It's neither required or explained by the known laws of physics, and of course, that bothers people. All we know is it is comparable to the attractive force of gravity. This is a good thinking question. Dark energy. Is it a real thing? Is something actually happening out there that we don't know or understand? Or possibly. We don't know or understand everything in the bottoms of our oceans, so why wouldn't it not be possible that there's something out there that we don't quite get? But this additional vacuum pressure, or the cosmological constant, is what many cosmologists believe is what's actually going on. If you want to keep up with the debate about this, there is plenty of between TED Talks and published research that you can actually look up using the HCC database. I believe you have access to a lot of the papers if you are so interested and inclined to read about it. There's also podcasts that cover this information constantly where they're learning about the new things and bringing it out to non-scientists and people who actually want to know what's going on. There's books that have been published and there are constant media reviews. I'm sure there's also a couple YouTubers out there who are trying to explain it to the non-scientist part of the world who is curious about what dark energy is and the expansion of the universe. Totally encourage it. Based on this, astronomers have been able to create this graph based on what we know of the composition of the universe. 5% of the universe is normal matter. Planets, stars, gas, molecules, dust, these cosmic windows, nebula, baby stars, adult stars. That's all normal matter. Then we have 27% is dark matter, which involves white dwarfs, brown dwarfs, red dwarfs, black holes, things we can't see, but we know are there. And then there's dark energy, something we can't measure. We just know that there's this repulsion happening in basically empty space. Here the universe without energy is represented by the red, purple, and blue lines on this graph. It decreases for larger values than present-day density. The age of the universe depends on its composition, is basically what it boils down to. We know its present size, but in order to extrapolate backwards to zero size, we need to know how it got to be the size it is now. Previously, we calculated the age of the universe to be about 14 billion years. With recent knowledge of dark energy, it may have expanded faster in previous years, making the universe much younger than we actually thought. The cosmic microwave background is a very important happy accident that was discovered by Arnold Penzias and Robert Wilson, who were scientists, believe it or not, at Bell Telephone, which now today we know as AT&T. They were designing an experiment to make America's telephone system better. Part of the project was also to get rid of this weird background static in satellite communications. While studying the radio wavelengths of the Milky Way, they noticed this bothersome background hiss, like background static on a radio station or white noise on your TV when you reach a channel that just goes shh. And no matter where they pointed their antenna, it kept coming, never weakening, never strengthening, all day, all year. And what was determined was that background hiss was the leftovers of the creation of the universe, which they dubbed the cosmic microwave background. This is known as the cosmic microwave background. If you remember the EM scale, microwaves are more towards the red side. They are below the colors we can see. Their wavelengths are pretty wide apart, meaning these photons are not as energetic. And they're probably still dropping in energy to become more, especially since they have now hit that radio wave frequency where they're just coming out as a hiss of static. So when these photons were first created, they would have been super duper energetic, probably gamma ray radiation energetic level. And over time, since the universe has expanded, and remember, as it's expanding, the wavelength is becoming wider as it is stretched, these photons would have redshifted basically to what they are now, radio spectrum background noise. The radiation today is the fossil remnant of the photons from the beginning of the universe. Now they are in the radio spectrum with a black body curve corresponding to about 3 Kelvin, which is actually cold. Since the cosmic background spectrum has been measured with great accuracy, we're actually able to really see its frequency with its wavelength and its intensity, which is really cool. Radiation in the universe is really important. It's how we really study the evolution of the universe, which is the role that it really plays. The total energy of the universe consists of both radiation and matter. And as the universe has cooled, it went from being originally a radiation-dominated universe to being a matter-dominated universe. Dark energy becomes more important as the universe has expanded. It is unimportant at the start of the universe, but definitely it dominates today. As the temperature of the universe fell below 900 million Kelvin about 2 minutes after the Big Bang, theoretically, conditions became favorable for protons and neutrons to fuse and form deuterium, a 1 proton and 1 neutron hydrogen. Prior to this, there was too much gamma radiation for the nuclei to stick around. They would essentially get torn apart. Remember, we were learning about those dark clouds that we can't see through, and that there's a whole bunch of molecules in there, and by radiation not being able to get into these clouds of dark matter, these molecules don't get torn apart. Well, same thing. If there's too much gamma radiation, those deuterium nuclei are not going to stick around. They're going to quickly get torn apart. But once deuterium was able to form and survive, other fusion reactions occurred, becoming heavier and heavier elements like helium and proper hydrogen. And so in a matter of minutes, the universe was mostly hydrogen and helium. Today, helium is formed in the hearts of stars through nuclear fusion. However, the production of elements heavier than hydrogen by nuclear fusion after the Big Bang is called the primordial nuclear synthesis. This ended about 15 minutes after the Big Bang, theoretically. Deuterium is not formed in stars. It doesn't happen. So any deuterium that we see today must be pre-star or primordial. The time during which the nuclei and electrons combine to form atoms is referred to as the decoupling epoch. During this time, the radiation background separated from the normal matter, and before the matter was ionized, forming hydrogen and helium, there were a lot of free electrons that interacted with EM radiation of all wavelengths. The universe was opaque to radiation. After helium and hydrogen formation, only certain wavelengths could interact with matter. So why are these problems? Why does this cause an issue? Thanks to cosmic inflation, we end up with these two issues, horizon problem, and the flatness problem. The horizon problem is the cosmic background radiation appears the same in diametrically opposite directions. Basically, that means here we are right here. If we were to look this way, we see X. If we were to look this way, we also see X. That's weird. There hasn't been enough time for the interaction between these two areas. So why do they look alike? Why do they both look exactly the same? You'd think you'd see X over here and Y over here, right? But we're not. We're seeing X and X. And then there's the flatness problem. In order for the universe to have survived this long, its density in the early stages must have differed from the critical density by no more than 1 part in 10 to 15, meaning the universe is essentially flat, but we don't have a reason that the universe would have formed with so much density in the first place. Why is this a problem? Because cosmologists want to be able to explain these phenomena rather than just accept them as is. Scientists have this problem. We don't like to look at something and say, okay, it just is. We like to go, why? Why are you like this? Let me pick you apart and find out your problem.
Right, so let's do a little bit of a visual for the horizontal problem, because I know this one's actually really difficult for people to understand. So think about it as you have two markers, and they're exactly the same. They're both expo green markers. And the idea is that if I look to my left, I see an expo green marker, and I look to my right, and I see pretty much the exact same expo green marker. I know these two markers should never have been in contact with each other. I know they also did not have enough time to have contact with each other. So why am I seeing pretty much the exact same expo marker on either side of me, many, 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 many light years away? This is the horizontal problem in a nutshell. What I'm expecting to see when I look this way is a green one, and when I look the opposite direction, I keep tapping green, is a red expo marker. This would make sense, because they shouldn't be the same. They should be two different things in opposite directions, okay? I should not be seeing two of the same.
In the 1970s and 80s, theoretical physicists succeeded in combining the strong force, weak force, and electromagnetic forces, creating a superforce. The general prediction of the grand unified theories that describe this superforce is that the three forces are unified and indistinguishable from each other only at enormously high energies, basically temperatures exceeding 10 to the 28th Kelvin. Otherwise, the superforce will split. Implications were discovered for the early universe using this less than 10 to the negative 34 seconds after the Big Bang. Parts of the cosmos would have found themselves unstable, in which they would simply face an acquired vacuum energy, basically becoming excited above its equilibrium state. And the appearance of this energy led to extra energy, causing the affected region to expand at an accelerated rate or hyperinflate to a factor of 10 to the 50th. This period, known as cosmic inflation, is also known as the epoch of inflation. After this, the universe returned to its normal expansion, and scientists realized that this situation could only occur under many different circumstances, and so could have happened many times during the beginning of the universe. Meaning, you could have had times of hyperinflation, normal, hyperinflation, normal, hyperinflation, normal. Do they know how many times this happened? No. Do they know if it could happen again? No. Do they know why it happened? Me. Grand unified theories. There are times when what theorizing is that the universe hyperinflated very quickly. What is the implication of this for the universe? Inflation would solve a lot of problems, particularly the horizon and flatness problems. Essentially, the two regions mentioned earlier in the flatness problem were at one point, so if we talk about the horizon problem, region X and region X, which look exactly the same in both directions, were at one point in contact with each other before the rapid inflation. Meaning, once upon a time, X and X were either on top of each other or right next to each other. And then because of hyperinflation, they got separated. This diagram shows how the flatness problem is solved. And because the universe is flat relatively, tells us that the total density must be equal to the critical density. Basically what this says is you have an ant on a balloon. It cannot sense the curvature. Just like when we were on the Earth, we can't sense the curvature unless we look into the distance. So we start here with, I can see the curve. Just like on Earth, we can see the curve. But now we have expansion so far that the curvature is so slight, it's a flat surface. And this leads us to the large-scale structure of the universe. Cosmologists have realized that galaxies could not have formed just from instabilities in normal matter. Before separating, background radiation kept clumps of normal matter from forming. Variations in the density of matter before separation would have led to variations in the cosmic microwave background. And dark matter, being unaffected by radiation, would have started clumping long before separation. Remember that dark matter helps keep whatever's inside it safe, all those molecules. Later, normal matter would have been able to clump in order to start forming stars and luminous galaxies. Galaxies could then form around the dark matter clumps, resulting in the universe that we see. And this explains why there is so much dark matter found outside visible galaxies. The luminous material is strongly concentrated near the density peaks and dominates the dark matter there, whereas the rest of the universe is, however, devoid of this normal matter, allowing for dark matter to then be more prominent. Although dark matter does not interact directly with radiation, it will interact through the gravitational force, leading to these little tiny ripples in the cosmic background radiation. And this is what it looks like when these ripples have been observed.
And that's all for Lecture 17. I hope you guys have enjoyed it, and I will see you next time.